Okay, today we're going to be looking at tutorial 4a, which is a constrained optimization problem with a linear constraint. Consider the function g, which is a function of x and y, is equal to x multiplied by y, and the constraint f of x and y is equal to b minus x minus py for some value of p which is greater than 0, and for some value of b which is also greater than 0. Write down the Lagrangian for the optimization problem, the maximum of this function subject to this function. Cool, let's get started. Okay, so the Lagrangian function is defined by a function which has variables x, y, and lambda, and is equal to f of x, y minus lambda g of x, y. So f of x, y is the function we want to maximize, and then g of x, y is our constraint, so subject to this constraint. So we have a function we want to maximize subject to this constraint. In our question, f of xy is g of xy because that's what we would like to maximize, and our constraint is this function f of xy. So if we now write that down, we get g x comma y minus lambda f x comma y, which is equal to xy minus lambda b minus x minus py. If I now just expand those brackets, which we don't have to do, but I feel it might make it easier when we go on to working out the partial derivatives, we get minus yb plus lambda x plus lambda py. Cool. Moving on to calculating the first order conditions. We'll first differentiate the Lagrangian with respect to x, so this will be a partial derivative. We will get y when we differentiate that, and then plus lambda when we differentiate that. And of course our first order conditions are equal to 0. Moving on, if we differentiate with respect to y this time, again a partial derivative, we will get x plus lambda p. So this part will differentiate to x, and then over here we get lambda p. And again, this is also equal to 0. And if we differentiate with respect to lambda, because that's another variable, we get minus b plus x plus py, and that's also equal to 0. Hopefully you can see that from here. Now, in order to solve the first order conditions, I shall rewrite them. So we have y is equal to lambda, y plus lambda is equal to 0, which I'm going to label as equation 1, x plus lambda p, which is also equal to 0, which I'll label as equation 2, and then our budget constraint, which is minus b plus x plus py is equal to 0, and that's going to be our equation 3. If I make lambda the subject for equation 1, we get lambda is equal to minus y. Doing the same for equation 2, we get lambda is equal to minus x, so moving that to the other side, and then we divide by p, so minus x divided by p. If I now equate these two functions together, we get minus y is equal to minus x over p. Now this is the same as y is equal to x over p. Using this, I am going to substitute this equation, which I'll label 4, into our equation 3. So sub equation 4 into equation 3, we get minus b plus x plus p brackets x over p is equal to 0. These p's cancel out, so we get minus b plus x is equal to 0. So 2x is equal to b if I move that to that side, and x plus x is 2x, and then x is equal to b over 2. Now that we know x is equal to b over 2, we can find out y by using our equation 4. So y is equal to b over 2 divided by p, which is equal to b over 2p. So we get y is equal to b over 2p. To find out lambda now, we can use either of these equations. Lambda is equal to minus y is, of course, easier. So lambda is simply equal to minus b over 2p. So just a negative sign in front of this. So writing that in, our solution is lambda was equal to minus b over 2p x was equal to b over 2, and then y is equal to b over 2p. Cool. Moving on. Calculate the bordered Hessian and determine the nature of the global optimum. So now we're going to see if the solutions that we got from making the first order condition 0 was a maximum or a minimum or a saddle point. In order to do that, we calculate the bordered Hessian. The bordered Hessian looks like this. So we get 0 in column 1, row 1, and then partial derivative of our budget constraint, or just our constraint, with respect to x, and then with respect to y, and that repeats over here. And then we just have our normal Hessian. So the second derivative of the function with respect to x, and then our second derivative differentiated partially with respect to x and y, and then over here y and then x, and then our second derivative of y. And there's our bordered Hessian. A normal Hessian matrix would just be these four elements. So if I write down the Hessian, that would be the second derivatives of a function. So it looks something like this. What the bordered Hessian does is shows us the second derivatives, how to squeeze that in, and its eigenvalues, tells us if the optima is a max, min, saddle, or if it's undetermined. A bordered Hessian is doing the same thing, but it's taking into account the constraint that you put on a function. So in this question, we had a constraint which was b minus x minus py. So the bordered Hessian takes that into account when trying to determine the nature of the optimum. So if we work out the bordered Hessian, so this stays a 0. Our function g is our constraint, and our constraint was b minus x minus py. So if we partially differentiate that with respect to x, we get minus 1. And if we partially differentiate that with respect to y, we get minus p. And that is the same over here. If we now find the second derivative of the Lagrangian, going back up to this point, if we differentiate this again with respect to x, we simply get 0. If we differentiate that with respect to y now, we would get 1, and that's the same over here. Differentiating this function with respect to x would give us 1, because this x would differentiate into 1, and differentiating the function of y, again, this function would get 0, because there's no y present, so 0. So this would be our bordered Hessian, if I just now fill that in. Cool. In order to determine whether the nature of the optimum is a maximum, minimum, or saddle point, we will have to work out the determinant of the bordered Hessian. So with the normal Hessian, you looked at eigenvalues. With the bordered Hessian, you look at its determinant. So to work out the determinant of a 3x3 matrix, we can pick any row. I'm going to pick this middle row, as I see it as the easiest. And from there, we look at the matrix of minors for every entry on this row. Another thing we also do need to consider is this matrix, which says that whatever this value is, we will negate it. So we have, instead of -1, we'll have +1. So 1 minus -1. And then the matrix of minor for this entry would be when we ignore this row and ignore this column, and we see what elements are left. So that would be -1, minus p, 1 and 0. So -1, minus p, 1 and 0. Doing the same thing for 0, and it's plus, so +0. Ignoring this row and this column, what's left behind is 0, minus p, 0. So that would be the matrix of minors. So we'd get 0, minus p, 0. And then lastly, this, which has to be negated. So it'd be -1. And the matrix of minor would be 0, -1, minus p, 1. If we now work out the determinant, we get 1, and then 0 minus p, plus 0, 0 minus p, p squared minus 1, 0, minus p. So here we are left with 0 minus p, which is just p. When we times by 0, this just gets eliminated. And then minus 1 times this minus p will just be positive p. So plus p. So we're left behind with 2p. Now, as p is greater than 0, the det of the bordered Hessian will also be greater than 0, because 2 times any positive number will be another positive number. Therefore, as the determinant is greater than 0, the optimum is a maximum. Okay, use Mathematica to visualize the isoquant g, which is a function of the vector x, through the optimum. And then use Mathematica to visualize the constraint f, which is a function of the vector x, and it's equal to 0, and then the gradient flow of g, which is a function of x and y, and sketch the results below. Okay, in order to do this, I'll first write down our function gx comma y, which was x multiplied by y, and then our constraint, which was f of x and y, which was equal to b minus x minus py. Okay, in order to do this on Mathematica, we need to use contour plot. But before we use contour plot, we first need to find the isoquant of this function through the optimum. In order to do that, we must sub in the optimum values. So we got the optimum value of x was b over 2, and then the optimum value of y was equal to b over 2p. If we now multiply those together, we get b squared over 4p. So we would have to draw xy is equal to b squared over 4p. For simplicity, I am going to be saying b is equal to 1, p is equal to 1 as well. So we get xy is equal to 1 over 4. Hopefully you can see this is just a reciprocal graph, so 1 over 4x. So we will have to draw this. Looking at the constraint, which is equal to 0, we have 0 is equal to b minus x minus py. Again, b is equal to 1, p is equal to 1. So we get 0 is equal to 1 minus x minus y. Moving x and y to the other side, we get x plus y is equal to 1, which if we rearrange to make y the subject, is just y is equal to 1 minus x. If we now do a rough sketch of this, we will get something which will look like this. So this is xy is equal to a quarter, and then this is x plus y is equal to 1, and this is our optimum value. In order to work out the gradient flow of the function g, which is a function of x and y, we will need to work out gradient. So the gradient of this function will be equal to the partial derivative of x and then the partial derivative of y. So we get y comma x when we do that. What this means is that the arrows in the flow point in the direction y comma x at each point xy. What I'm going to do is draw y is equal to x just temporarily. Now let's say we had a point 4, 5. This is going to point in the direction of 5, 4. So we start at 4, 5 and draw an arrow pointing towards 4 plus 5, 5 plus 4, which is equal to 9, 9. So we have an arrow, 4, 5, which points in the direction of 5, 4, which ends up being 9, 9. So if I draw this point as 4, 5, just completely randomly, and then this point as 9, 9, this arrow would move something like that. And that's the case with all of these arrows. So we have a gradient flow which looks something like this. I will attach the Mathematica code and the stream plot in Mathematica so that it's a more accurate representation of what the stream or what the gradient plot should look like, but hopefully that makes a bit of sense if you did have to do this manually without Mathematica. Okay, we're now going to be looking at the constrained optimization problem on Mathematica. So the question one was, we had a function g of xy which was equal to x multiplied by y, subject to the constraint f of xy which was equal to b minus x minus py, and p is greater than 0 and b is greater than 0. The last question of this problem was use Mathematica to visualize the isoquant of g of xy through the optimum, to visualize the constraint when it's equal to 0, and to visualize the gradient flow. But before we get to that, we're going to work through this whole question through Mathematica. So if we were to write some pseudocode for that, what we have to do is first define the function gx of y and define the constraint f of xy. Step 2 would be to then find the Lagrangian function using the formula which we saw before. Step number 3 would to then be work out the first order conditions and solve them to find the optimum value for the constrained problem. Step number 4 would be to calculate the bordered Hessian and determine the nature of the optimum using the determinant. Step number 5 would to then call the function g of xy again and substitute the optimum values to find the isoquant through the optimum. Step number 6 would to then be to draw the constraint and the function g of x, y using the contour plot command. And lastly, we have to draw the gradient flow of g of x, y using the stream plot command. And before we do that, we will have to work out the partial derivatives of g of xy in order to draw the gradient flow. So that's the process that we are going to be working through. If we now go on about coding this, so define the function g of xy and define the constraint. In order to do that, we have g x, which is a variable, comma y, which is also a variable, is equal to x multiplied by y. And then the constraint is f, which is a function of x, and y, which is equal to b minus x minus p multiplied by y. Now that we've defined our functions, we are going to define the Lagrangian function. So the Lagrangian function is a function which is a variable which has variables x, y, and lambda. So x, y, and lambda. So that would be escape L escape. And this is equal to g of x, y minus lambda f x comma y. So now we need to work out the first order conditions. In order to do that, we must differentiate the Lagrangian function with respect to x, and then we also need to differentiate this with respect to y, and differentiate this with respect to lambda. Then what we have to do is solve these three equations that we will get in order to find the optimum value for the constrained problem. In order to do that, we use the solve command. So solve these three equations. These three equations will be equal to 0 because first order conditions are always equal to 0. So we're solving these three functions, which are all equal to 0. Because we have a list of functions, we are going to be using the curly brackets, and we are solving them with respect to the variables x, y, and lambda. X, y, and lambda. Cool. Just as a word of note, we should make it very clear that it's lambda times this function. Okay, now that we have solved these solve the first order conditions, we can move on to working out the bordered Hessian. Like I mentioned before, the bordered Hessian has the Hessian within it. So let's begin by working out the normal Hessian. So h for Hessian will be equal to the derivative of the function gxy, and we are differentiating this function with respect to both x and y, and we're doing that twice because we're working out the second derivative. So this would give us our Hessian. Okay, if we now run all of this code just to make sure that everything is running smoothly, we can see that we get x is b over 2, y is b over 2, b over 2p, and lambda is minus b over 2p, which was what we got before. And the Hessian is 0, 1, 1, 0, which is also what we got before, which is fantastic. If we continue onwards, we have to now work. So to work out, if I just add this in, to work out the bordered Hessian, we need to differentiate the constraint, as the bordered Hessian takes into consideration the constraint when determining if the solution is a max, min, or saddle point. So as a result, we now need to differentiate f of x, y with respect to x and y. So in order to do that, so this is going to be the gradient of f, which will be equal to the derivative of the function f x y, and we are differentiating this with respect to x and y. You might notice that there's two curly brackets. That's just because the two curly brackets tells Mathematica to differentiate once with respect to each variable. So Mathematica will differentiate this with respect to x, differentiate it with respect to y. Now, if we work out the bordered Hessian, so I'm going to label this mat. There is probably much better ways to do this. However, I am not that proficient in Mathematica, so this is the only way that I could figure out how to do it. I'm just going to manually write the bordered Hessian. So we know that the first entry in the bordered Hessian is 0. The second entry would be our budget constraint, partially differentiated with respect to x. So in order to call that from this piece of code, we'd have to do gradient, so grad f, so this variable, and we're calling the first thing that this computed, which would be the partial derivative of f with respect to x. And then the third thing in the first row would be this function, but now partially differentiated with y. That would be the second thing that this piece of code computed. So we do graph f and then 2. So this is the first row of our bordered Hessian. Moving on to the second row. The second row would have grad f 1, and then it would have this 0 from the Hessian. In order to get that 0, we would have to write h, because h represents Hessian in this piece of code. And we need to call this first list, and within this first list, we need to call a first thing. So it'd be 1, 1 to call the first list and the first thing in that first list. Then we need to again look at the first list, but now call the second thing. So it'd be 1 and then 2, and that would give us the 1. And all of this is going to be our second row of a bordered Hessian. For the last row, we have gradient function of f, and we want 2 this time, because that will give us the partial derivative of y. The next thing we want is this 1 from our Hessian. In order to do that, we now want the second list and the first thing in the second list. So we have Hessian 2, 1, and we also want the last thing, which would be second list and then the second thing in that list, so 2, 2. If we now run that, here is our bordered Hessian. To make that into a much nicer matrix form, we will use this command. So mat and then two dashes, matrix form, and we get 0 minus 1 minus p, minus 1 0 1 minus p 1 0, which is what we got for 0 minus 1 minus p, minus 1 0 1 minus p 1 0. Now that we have the bordered Hessian, we can see if our values for x, y, and lambda are a minimum or maximum. In order to do that, we have to work out the determinant. So the determinant of the bordered Hessian is equal to the depth of the matrix mat. And so we're using an if command, if we assume that p is greater than 0, because that's what's given in the question, we can simplify the determinant when it is greater than 0. And when we do this, if this comes out... Okay, so what this code is saying is that we're going to assume p is greater than 0, and when p is equal to 0, we're going to simplify the determinant. And if the determinant is greater than 0, then our point is a maximum. If it is not, then our point is a minimum, is what this line of code is saying. So if we now shift enter, we get the determinant as 2p, and because it's 2p, when p is greater than 1, we would have 2, 4, 6, and so it's always going to be greater than 0, hence why the if statement churned out maximum here. So far we have defined the function and defined the constraint. We have defined the Lagrangian function. We have solved the first order conditions and find the optimum value. And we have calculated the bordered Hessian and determined the nature of the optimum. So next step is to call the function g of xy and substitute the optimum values to find the I-squant through the optimum. So call the function, so g of x, y, and we are going to replace, so this stands for replace all, so that just means replace the x and y with our solution. So if you remember, this gave us our solutions. So if I now make this equal to solution, so this is now a variable, we can take our solutions and put them into this function g of x, y. So take our solutions and place it into x and y. And if you notice, it's a list within a list, so we want this first thing, hence why I've got that one there. So if we again do shift enter, when we equate these, or when we substitute these solutions into this function, we get b squared over 4p, which is what we got last time as well. If I now let b and p take some numeric values, for simplicity, I will use 1 and 1. We can now start plotting. So we have done this, and we are now going to draw the constraint and the function g of xy using contour plot. I'm going to label this value, so b squared over 4p as s, and you will see why soon. If we use contour plot, we have the function g of x, y, and I'm going to make that equal to s, so this value, because that would give us the I-squant of where g of x is the optimum. And I'm also going to draw the budget constraint, so f of x comma y is equal to 0. So the curly brackets were used here because this is a list of different functions. Now to define the range and domain, I'm going to keep it simple and just do 0 to 10, and the same with the range, so 0 to 10. So that's my contour plot. If I do my stream plot, before I do my stream plot, I will have to work out the partial derivatives of the function g of x, y. In order to do that, I will have to do derivative of g of x, y, and I'm going to be differentiating that with respect to x and then with respect to y. So exactly the same as what we've done over here. I'm going to label this grad g, and I'm also going to label this as a Okay, if we now begin drawing the stream plot, in order to, so stream plot is used to represent the gradient flow. So stream plot, the gradient function of g, and with domain between 0 and 10, and the range between 0 and 10 as well. And I shall label this A, and then I will show A. Oh wait, I can't label it A. We'll label it T. I'll label, and I will show A and T on this same graph. So now if I do shift enter, starting from the beginning, we have our optimum values, which Mathematica found. We have the Hessian. We then have the partial derivatives of the budget constraint. We then have the bounded Hessian and the bounded Hessian in a more nicer matrix form. We then have the determinant of this matrix form, and using this determinant we have shown that this optimum is a maximum as the determinant is greater than 0. We then have b squared over 4p, which represents the value of the function g(xy) when we substitute in the optimum. And then we have 1, 1, which is simply just what I've decided be the parameters b and p to be. And then the contour plot did not work because I've spelled it wrong. Contour plot, yeah, that should now work. So 1, 1, and then the contour plot now works, and this is what we get. We get a reciprocal graph, and then over here is our constraint line, and then y, x represents partial derivatives of our function g of x, y, and then we have the stream plot, which shows that the direction of increasing gradient is northeast, and putting these two graphs together, we get this. So this is what you would draw for part C of this question. Hopefully that all made sense. Cool, moving on. We have a constraint optimization with a non-linear constraint. Consider the function g x of y is equal to xy, and the constraint f of xy is equal to r squared minus x squared minus p y squared for some value of p which is greater than 0, and some value of r which is also greater than 0. Write down the Lagrangian for the optimization problem where we want to maximize this function subject to our constraint, which is r squared minus x squared minus p y squared. So this is the exact same as before. So we have the function g, which we want to maximize subject to our constraint, which is f of x, y. So this equals xy minus lambda r squared minus x squared minus py squared. If I expand the lambda out, we get xy minus lambda r squared plus lambda x squared plus lambda py squared. And that is our Lagrangian. If we now move on to the first order conditions, we differentiate the Lagrangian with partially with respect to x, and we get y plus 2 lambda x is equal to 0. Differentiating it partially with respect to y, we get x plus 2 lambda py is equal to 0, and differentiating it partially with respect to lambda, we get the constraint, so minus r squared plus x squared plus py squared equals to 0. So now if we go about solving this, if I rewrite our first order conditions, so y plus 2 lambda x is equal to 0. This is going to be our first equation. X plus 2 lambda py is equal to 0 will be our second equation, and then minus r squared plus x squared plus py squared is equal to 0 is our third equation. Like before, if I make lambda the subject, we get lambda is equal to minus y over 2x for equation 1, and for equation 2 we get minus x over 2py. If I now equate these two together, we get So equation 1 equal to equation 2, we get minus y over 2x is equal to minus x over 2py. If we cross multiply, we get 2x squared is equal to 2py squared. So we get x squared is equal to py squared. If we label this equation 4 and sub in equation 4 into our constraint, which is equation 3, we get minus r squared plus py squared plus py squared is equal to 0. So we get 2py squared is equal to r squared. So y squared is equal to r squared over 2p. And so y is equal to plus or minus r over root 2p. If I now use y is equal to minus y over 2x to find, if I now use this equation to find our values of x, let's start off with y is equal to r divided by root 2p. So we get x squared is equal to py squared, and then x squared is equal to p multiplied by, if we can just use this because this is y squared, p multiplied by r squared over 2p. So x squared is equal to r squared over 2 when we cancel out the p's. So x is equal to plus or minus r over root 2. So when y is equal to positive r over root 2p, we get two solutions of x. So if we label this as our first solution, we get r is equal to r over root 2, y was r over root 2p, and then we will find the value of lambda soon. If we have our second solution, we have minus r over root 2p, so this is our negative x value, and y was r over root 2p, and then some value of lambda, which we will find at the end. Doing the same thing for when y is equal to minus r over root 2p, substituting it into the same equation, x squared is equal to py squared. We get x squared is equal to p multiplied by r squared over 2p. So x squared is equal to r squared over 2. So x is equal to r over root 2 and plus or minus. So if I just move these, over and have solution number 3, we have r over root 2 minus r over root 2p, and then lambda, and then 4 r over minus r over root 2 comma minus r over root 2p, and then some value of lambda, which we will work out. So we have 4 solutions for our first order conditions. If we now work out lambda, we can use minus y divided by 2x. So if we do that for equation 1, we have minus r over root 2p, so that's our minus y, and then divided by 2x. So divided by 2r root 2. When we do that, we get minus 1 over 2 root p, because this root 2 and this root 2 gets cancelled, so what's left behind is root p over here. So we get minus 1 over 2 root p. If we do the same thing for solution number 2, we have a negative y multiplied by a negative x. So we will get a positive value, so it's positive 1 over 2 root p. When we do this for solution number 3, we get a positive x plus a positive y, so we get positive 1 over 2 root p. And when we do it for equation 4, we get positive y, but then a negative value for 2x, so we get negative 1 over 2 root p. Hopefully that makes sense. If we now fill in the solutions, we have minus 1 over 2 root p, and then for x we have r over root 2, and then r over root 2p. So that's our first solution. For our second solution, we have 1 over 2 root p, r over root 2p, and minus r over root 2. For our third solution, we have 1 over 2 root p plus r over root 2, and then minus r over root 2p. We just realised that these two should be swapped around, so we have minus r over root 2 for x, and then r over root 2p for y. And then our last solution was minus 1 over 2 root p minus 3 over root 2, and minus r over root 2p r. Okay, cool. So these are all our 4 solutions. If we go on to calculate the bordered Hessian for the general lambda x and y, and then determine the nature of the optimum. If we begin by defining the bordered Hessian, it was 0. We used the function f because f was our constraint. If we begin by solving this, we have 0. Our function x comma y was equal to r squared minus x squared minus py squared. So we have, when we differentiate that partially with respect to x, minus 2x. When we differentiate partially with respect to y, we get minus 2py. That's the same over here, so minus 2x, and then minus 2py. If we now differentiate our first order conditions again, differentiating this with respect to x, we get 2 lambda. Differentiating this with respect to y, we get 1, and that's when we differentiate this with respect to x, we also get 1. So both of these are 1, so 1 and then 1. And then differentiating this partially with respect to y, we are left with 2 lambda p. So 2p lambda. So that would be our general bordered Hessian. If we now work out the nature of the optimum for our individual solutions, if we begin with our first solution, we had r over root 2, comma r over root 2p, comma minus 1 over 2 root p. So if I substitute these values into our general bordered Hessian, we get 0 minus 2r over root 2 minus 2rp over root 2p minus 2r root 2 minus 2pr over root 2p, and then minus 1 over root p minus 1, 1 minus 2p over 2 root p. If I now just simplify this matrix, so 2 over root 2 is just root 2, so this simplifies to minus root 2r. Simplifying this, again 2 over root 2 is just root 2, so we get minus root 2. P over root p would be root p, so we get finally root 2r root p. Simplifying this, 2 over root 2 is just root 2, so we get minus root 2r, and again we get this, so minus root 2r root p. We can't do anything to minus 1 over root p, and minus 1, and then minus 1, and minus 2p over 2 root p, the 2's cancel out, and then p over root p is just minus root p. So that would be this Hessian simplified. If we now work out the determinant of this Hessian, I will just use this top row. We get 0, and then the matrix of minor would be minus 1 over root p minus 1 minus 1 minus root p. And then we get minus root 2r, but this will change to a positive sign because of this matrix. So positive root 2r and the determinant of the matrix of minor, which is minus root 2r, 1 minus root 2pr minus root p. And then minus root 2pr. So I'm just connecting up the root 2 and the root p. And then the matrix of minor would be minus root 2r minus 1 over root p minus root 2pr and 1. So what is left behind is 0 plus 2 plus root 2r. And then when we find the determinant of this matrix, we get root 2pr minus root 2p r, and then minus root 2p r minus root 2r minus root 2r. Because that multiplied by that is positive root 2r, and then the determinant is AD minus BC. If we now simplify this a bit more, we get root 2r is brackets 2 root 2pr, because this ends up being plus, and then minus root 2pr minus 2 root 2r. And then this simplifies to 4 root p r squared, because when we do root 2 times root 2, we just get 2, and then 2 times 2 is 4. So 4 root p r squared minus the same thing happens over here. So minus 4 root p r squared. So we get 8 r squared root p as the determinant of this bordered Hessian. Now, as r is greater than 0 and p is greater than 0, the determinant of HB must be greater than 0, and that means that the optima is a maximum. So this is a maximum. If we now do the same thing for solution number 2, we have x, y, lambda. X was minus 3 over root 2, y was 3 over root 2p, and lambda was 1 over 2 root p. So the Hessian is going to look very similar, but just with a few sign changes. So we still get 0 over here. So if I rewrite the bordered Hessian, the general bordered Hessian, we had 0 minus 2x minus 2py minus 2x 2 lambda 1 minus 2py 1, and then 2p lambda. And if I also write down our simplified bordered Hessian that we got for solution number 1, it was 0 minus root 2r minus root 2pr minus root 2r minus root 2pr. And our solution was a positive, and then a negative. So now, when we work out the Hessian for this solution, this is still going to remain a 0. As we now have a negative, positive, this is just going to be positive root 2r. This remains the same as y is still positive, so we still get minus root 2pr, and that follows over here. Y is now going, 2 lambda will now be positive, so it'd just be 1 over root p, and we have 1, and then 2p lambda will also be positive now, so it'd just be root p. So now, if we work out the determinant of this bordered Hessian, again using the top row, we have 0, and it doesn't really matter what the matrix of minor is for this element, so we can just not write it in, and then minus root 2r. The matrix of minor is root 2r 1 minus root 2pr root p, and then minus root 2pr root 2r 1 over root p minus root 2pr and 1. So if we start working out the determinants, we get minus root 2r, and then root 2pr minus turns into a plus root 2pr, and minus root 2pr root 2r minus turns into a plus root 2r. Hopefully you can follow that. Simplifying this, we get minus root 2r, 2 lots of root 2pr minus root 2pr, and then 2 lots of root 2r. Multiplying this, we get minus 4 root p r squared, and again minus 4 root p r squared. So our final answer is minus 8 root p r squared. Again, as p is greater than 0 and r is greater than 0, the determinant will be less than 0. Therefore, the optimum is a minimum. Cool. If we now move on to solution number 3, so x, y, and lambda, we had r over root 2 minus r over root 2p, and then 1 over 2 root p. So again, if we work out the bordered Hessian, this stays as 0. If we compare this bordered Hessian with this solution, we had negative, positive, positive. This time we have a positive, negative, positive. So this will change. It will now be negative root 2r. This will change. It will now be positive root 2pr, and that follows over here. This won't change because both lambdas are still positive, so we still get 1 over root p, and 1, and then 1. And again, this will not change because both lambdas are still positive, so we get root p. If we now work out the determinant of this matrix, we get 0. In this matrix, we don't need to write down, but hopefully you can see it will be the entries of this. So 1 over root p1, 1 root p, then positive root 2r minus root 2r, 1 root 2pr root p, plus root 2pr minus root 2r, 1 over root p, root 2pr 1. So now if we work out the determinants, we get minus root 2pr minus root 2pr plus root 2pr minus root 2r minus root 2r. If we now simplify this, we get minus 2 lots of root 2pr plus root 2pr minus 2 lots of root 2r. Expanding the brackets, we get minus 4 root pr squared, and again minus 4 root pr squared. So once again, we get minus 8 r squared p, and just like last time, as r is greater than 0, p is greater than 0, the det is less than 0, therefore it's a minimum. Moving on to our last solution, we had minus 3 over root 2 minus r over root 2p minus 1 over 2 root p. So this time everything is a minus. So the bordered Hessian looks like 0 root 2r root 2pr, and that follows over here. And we have minus 1 over root p, 1, 1, and then minus root p. Again, working out the determinant and using the top row, we have 0. Once again, this matrix does not matter. Minus root 2r, root 2r, 1, root 2pr, 1, minus root p, plus root 2pr, root 2r, minus 1 over root p, root 2pr, 1. If we now work out the determinants, we have minus root 2pr minus root 2pr plus root 2pr root 2r minus plus root 2r. So AD minus BC. This time this was a negative, but then negative makes it positive. If we now simplify, we have minus 2 lots of root 2pr plus root 2pr and then 2 lots of 2 root 2r. Expand this out, we get positive 4 root pr squared plus 4 root pr squared. So now we get 8 root pr squared, and as r is greater than 0 and p is greater than 0, the determinant is going to be greater than 0, therefore we have a maximum. Cool. And moving on, use Mathematica to visualize the isequant of g, which is a function of x and y, through the optimum, the constraint f, which is a function of x and y, is equal to 0, and then the gradient flow of over g of x, and sketch the result below. If we remind ourselves of these functions, g x comma y was xy, and then fx comma y was equal to r squared minus x squared minus p y squared. So through the optimum, I'm just going to use one of the optimum, and I'm going to use r over root 2 comma r over root 2p with the lambda value of minus 1 over 2 root p. So again, for simplicity, I'm also going to be taking r is equal to 1 and p is equal to 1. So then we get, when we do x multiplied by y, 1 over root 2 multiplied by 1 over root 2, which is just a half. So xy is equal to a half. And rearranging this to make y the subject, we get 1 over 2x. If we now sub r is equal to 1 and p is equal to 1 into our constraint, we get 1 minus x squared minus y squared, and the constraint is equal to 0. So then we get 1 is equal to x squared plus y squared. So hopefully you can tell that this is a circle, or the equation of a circle with radius 1. If we now get drawing, just a rough sketch, we have y, x, 1 over 2x will look something like this. And then the equation of the circle, if I just draw a quarter of the circle, it would look something like this. And so finally, we are left with a curve that looks something like this, where this is gx, comma y, and this is our constraint, f of xy. To draw the gradient flow, as this is just the same function that we saw before, the gradient will be the exact same as before, and hence we have the gradient flow, which will look something like this. I will put up the code and some pictures of what this looks like on Mathematica. Okay, unfortunately the audio corrupted for this part, so I'm going to do a voiceover. It might not fully align with what's going on the screen, but it roughly makes sense. So the pseudocode is going to stay the same when we look at the constraint optimization with the nonlinear constraint, because the pseudocode just tells us a method on how to go about solving this problem. Because of that, the function gx of y is the same. The budget constraint is going to change. It's now r squared minus x squared minus p multiplied by y squared. So I'm changing that to the new constraint. The Lagrangian function and the first order derivatives are going to be the same. So is the Hessian, and so is the gradient function. The bordered Hessian will always be the same. We're just going to take what we did last time, and the determinant is just our determinant of the bordered Hessian. If I now ignore b is equal to 1 and p is equal to 1, just for the time being, and shift enter now, we can see that we get our full solutions. The solutions are a bit wrong because Mathematica still remembers that p is equal to 1, hence we can't see that root p. So now I'm just going to clear all previous memory, and then hopefully I will shift enter again and we can see the solutions when Mathematica doesn't know what p or b is actually equal to, and it treats it as a parameter. So shift enter again, we can see that we have x is equal to minus r root 2, y is equal to minus r root 2 root p, and then lambda is equal to minus 1 over 2 root p, which is what we saw when we did the question manually, and we have our other four solutions. If we now look at the determinant of the bordered Hessian, it is 8pxy. So going back to our if statement, so if assuming p is greater than 0, simplify the determinant. Because the determinant is now a function, I guess, or it's a value which has x and y, that if statement no longer is true because we need to sub in the x and y's that we get from solving the first order derivatives. That's quite a long-winded process, and because this video is already far too long, I've decided not to include that in. So I'm just going to get rid of the if statement for this question, as you can see. Now moving on to contour plot. Before that, I'm only going to be drawing the isoquant for this first solution, which is minus r over root 2 and minus r over root 2 root p. So summing those two values into g of xy, and I should get some value, and that value is r squared over 2 root p. And now if I, once again, if I now give values to R and P, because from before we didn't see anything in the contour plot, so I've decided on 5 and 3 randomly. And if we shift enter, we see that this is our isoquant. So we have the blue curve, which is g of xy, and then that ellipse is our budget constraint. If I change the domain of range so it's 0 to 10, we get something that looks a bit more familiar. So this is just me showing all the lines of code. So we got 25 over 2 root 3 when we subbed in the first solution. And that blue line is g of xy, and then the yellow line is our budget constraint. So this is just when we change the domain of range between 0 and 10. Here is our stream plot, or the flow of the gradient, which is the exact same as what we saw last time, because g of xy is still the same function. And if we show both of those on the same graph, we get that. If I now change R and P to 1, 1, we get, Mathematica still hasn't quite done this quite correctly, so we're going to press Shift Enter again, and here we go, we get the radius, we get a circle, sorry, with radius 1, and then we get that isoquant g of x, y, that blue line, which is pretty much what we drew before without Mathematica. So because we created this framework, all we had to realistically do is just change that budget constraint, and that was that. We were able to obtain the contour plot and the gradient flow. Cool. Hopefully that all made sense.